Okay, so we're going to discuss in this portion class 9 chapter 8 motion. So before we go to the main topic, we're going to discuss this portion so you can write it down. Okay, so first we will start with our systems unit. Now what do we mean by the systems unit? Okay, so here in the earlier times, people around the world use certain units that we're going to discuss called the systems units. Okay, so what do we mean by systems unit? For example, if you go to a shop and ask what is the price of this pen to the shopkeeper, and the shopkeeper replies it is rupees 10. So there, because he add the rupees, there is a meaning to that, right? If he were to just tell you 10, then you might get confused, right? What 10, like that, right? So units are those things that give meaning to numbers, right? Meaning to numbers. So like that in the olden times, in the earlier times, there were some systems unit that people used in order to give meaning to the transactions they're doing. Okay, 2 kg of aloo, okay, 3 kg of potato. That's whatever it is, the kg there, the unit kg there gives meaning to the quantity that you're buying. So units are such things that give meaning to the numbers that you're using, right? So the first system that they used, one of the systems that they used in the earlier times was called the FPS, okay, FPS system. Now, this FPS stands for measurement of length, okay, length or distance. We will use foot. That's what it means according to the FPS system. And for measuring mass, we will use pound, okay. So they use pound in this system to measure mass. And for measuring time, okay, time, we will use seconds. So that is the meaning of the FPS system, okay, that is foot, pound, second. So this was dominantly used in the UK, okay, in the UK by the British people, okay. Now there was another system unit, different system, that is called the CGS, that was very common and prevalent, okay, in the earlier times. So if you were to be using this CGS system, for example, then you would be measuring your length in centimeter. Then you will be measuring your mass in gram. And then you will be measuring your time in second. Then you are using the CGS system, right? Then there was another system of units called the MKS system, okay? So, for example, if you're going to use this for MKS system as your unit, suppose you're the one doing that, and you will be saying something like this, to measure the length of the veranda that I'm going to build, okay, how long my veranda should be when I build my house. I'm going to use meter, okay, meter. I'm going to use meter, the abbreviated small m, to measure 5 meter veranda. Then you would be saying, this evening to buy 2 kg of aloo. I will buy 2 kgs of aloo, kilogram. And then you would be saying, in the morning, I walk from my home to my school. What time do I take to reach the school? I'll measure in seconds. If you were doing that, that means you are using the MKS system, okay? So these were the 3 prevalent systems. They were all different systems, 3 different systems prevalent in the earlier times. But there was a problem with this because they were all different systems. Their confusion arose, okay? Why? Because, for example, there was some studies done in India, for example, by a scientist. And then there was a similar study done by a scientist in the UK. Then they wanted to exchange knowledge with each other. Then the scientist from the UK would be using foot as his length unit. And the scientist from India, let us say, is using meter. So 1 meter is around this much, we know that, right? And 1 foot may be around this much. So because they were different systems, confusion arose, right? So in order to solve this problem, what happened was, scientists, they met in France, okay? In France, they met and they decided like this. This is causing confusion to all of us. So let us make the whole world over internationally accepted system so that all of us can follow to avoid this confusion. So they brought out that system called the international system, which is simply abbreviated as SI system. Okay, and this SI system follows the MKS. That means for measuring length, SI system use meter, mass, kg, and time, second. So this is how they overcame the confusion of using different units. And nowadays, in the modern times, in our times, we use the SI system. So even in your textbook from chapter 8 to the next 4 chapters, 5 chapters are there in physics. Most of the units that we're going to use, we're going to follow the SI unit. Okay, so keep that in mind. And remember, SI unit follows the MKS system. Okay, so that is about the systems unit. So keep this in mind because this will keep on coming even as you go to higher classes. And it is good to get these things clarified from now itself, from class 9, right? Then you'll have no confusion as you go higher. Okay, so once we did with the systems unit, the next thing we want to do is we want to go to question number 6 on your tuition note. So let me write it down here, question number 6 here. What will that be? Because I feel that this is, if we discuss this first, it'll be easier for you. So differentiate, you write along with me. Differentiate between scalar and vector quantities. Okay, there are two types of physical quantities in the study of our physics, and they are called scalar and the other vector. Now, which one is which? Let us discuss. Now here, on the left side, make a margin, and on the left side, you make here scalar quantities. And on the right side, you make vector quantities. Okay, vector quantities. Now here, before we go any further, I want to add a side note here that might really help you. So here, there are two ways of learning. Okay, according to learning psychologists, there are two ways of learning: inductive versus deductive learning. So please write down along with me towards the bottom of your note. Okay, deductive learning. Now, what do we mean by this? You see here. Now, learning psychologists have found out that following this inductive way of learning is easier for students. Okay, so what do we mean by that? Let us start with an example. In the inductive approach, we start with a familiar example, an example that is so familiar to every one of us, and then slowly we begin to move to the more unfamiliar ones, like definition. Okay, definition, like technical definitions in the textbooks. If you go there directly, then it becomes hard, right? So we start from a very familiar example and then go to the more unfamiliar ones, like the definition. So let us do that. For example, in the scalar quantity, instead of saying defining scalar quantity, let us take an example that is very common to all of us. Let us say we are measuring height of a boy called, okay, John in your class. Height of John in your class. Now, if you were to measure his height, starting from his foot as 0, then 1 feet, 2 feet, 3 feet, like this to his head. Suppose he's 6 feet. Then you turn the meter tap and go the 0 to his head and measure it. By the time you reach the foot of the ground, the floor, he'll be the same height. What I'm trying to tell us here is that whether you measure the height of John from bottom to the top direction or from his head top to the bottom feet direction, doesn't matter. It's going to come out 6 feet only. So those type of quantities in which only the magnitude is important, those type of quantities which are defined by magnitude alone and the direction is not important or does not determine the quantity, are called scalar quantities. Example, therefore height of John, you can write down, is a scalar quantity. Okay, scalar quantity. Then let us take here an example of a vector quantity opposite to scalar. Okay, let me ask you this question. Do you open the door of your room 7-8 times in a day? Yes, right, because we have to go in and out of our room every day, right? So that is very familiar to you. That's the meaning of inductive approach, starting from something very familiar to you, like opening a door, right? So let us say you want to open a door. Now all of you go to your own room with your imagination. You see, physics is going to require a lot of imagination, okay? If you're willing to do that, then it's a very easy subject, physics, okay? So let us all imagine that how do you open, let us say in your room, in order to open your door, you have to pull it like this. And to close your door, you have to push it, right? Now in our lower classes, class 6, 7, we learned that, what is this called? You remember? I think you'll remember. Push and pull, right? It's called what? Yes, that's good. Force, right? Force. So we're going to take the example of force. Force is a vector quantity. Why? We will see right now. Height or distance is a scalar quantity because direction is not important, but force is a vector quantity. Why? See here. The force with which you will open your door, let us say the door in your room opens only when you pull it and you close it by pushing it. Then the direction in which, the direction of the force with which you open the door, let us say x Newton, with which Newton is the unit of force, okay? So with x Newton you pull the door, then only it's going to open. But the same force x Newton, if you were to push it, then the door will close, it will not open. So to open the door, not only the magnitude x of the force is important, but even the direction in which you apply the force is going to determine whether you open the door or not. So example, force needed to open my door, okay? My door, keep it as your door, then it becomes easy for you to understand, right? So the force that you need to open your door is in a particular direction. It's not like any direction you apply, like any direction you measure the height of John is okay, but any direction you apply the force to open your door, it's not going to be okay. It is a particular direction. So here direction, the amount of force, of course, important, but also the direction in which you apply the force is going to be so important, right? So those kind of physical quantities in which not only the magnitude but direction are also involved is called a vector quantity, okay? I hope you're getting it, right? Now let us now go and define. So this is called the inductive approach. You're starting with something very common, everybody can understand, height of a person, everybody can know that. Force needed to open my door, everyone can know that. And we start from the familiar one, now we're going to the unfamiliar one. The unfamiliar one here is the technical textbook definition. So let us try to define from here. So what is this? We can write along with me. Scalar quantity is a physical quantity, okay? It's a physical quantity. It's a physical quantity having only magnitude. The direction is not important, right? So this height of a person is a scalar quantity, right? Then here, number 2, this is 1, sorry. Here 2, vector quantity is a physical quantity, is a physical quantity, okay, having both magnitude. The magnitude is so important. Magnitude means 10 Newton, 20 Newton. That numerical value is called the magnitude. Okay, so having both magnitude as well as direction. So both of these together define a vector quantity. Magnitude plus direction define a vector quantity. Magnitude only or alone can define a scalar quantity. Okay. Now number 3. Here it changes, means scalar quantity changes with change in magnitude only, okay, only in magnitude only. So this height of John, 6 feet, will change only when you measure the height of a new boy, 5 feet 6 inches. So it will change only when the magnitude change, but the direction is not involved here, all right? But here you can change vector quantities. Vector quantities can be changed by many ways. Look here, it changes Okay, it changes by change in magnitude. When you change the magnitude only, also the vector quantity can change. So let us say 10 Newton is a minus 10 Newton is a force needed to open your door. Then you change only the magnitude. Minus 7 Newton is the force needed to change another boy's door. So just change the number and it will change. So magnitude alone. It changes by change in magnitude or direction. So only the direction alone also. For example, you apply 10 Newton. Now the door will close. So you didn't change magnitude, it's still same 10 and 10. But you change the direction plus, you see? You pushed it. So it will change by change in magnitude or only direction, or when you change both also. So there are three ways by which you can change a vector quantity. So let us see here. It changes by change in. First way is you change the magnitude and the vector quantity will change. Second way is you change only the direction, the vector quantity will change. And the third way is you change both, then also the vector quantity can change. But for scalar quantity, you change only, even if you change only magnitude, it will change. There's only one way by which you can change a scalar quantity, that is by changing the magnitude. Okay, so I hope you have learned something. We'll continue in the next class, the other parts. Okay.